Hello everybody. Hope you guys are doing well. So continuing on our journey, today we would be starting with deep databases. We'll try to understand, like basically we'll see what are the different properties that we have for databases, how to scale the bases, how to scale databases, why scaling is a important characteristics, like what is an SQL or what is an RDBMS, what is a NoSQL or SQL database. We'll see all that. So our goal is basically to cover as much as uh, databases as possible. So once you have that, then you will will go with move on to SQL. We'll write some queries and see which query is fast, which is slow. Okay. Now, so the whole talk about databases is basically three things, right? That we often deal with is, so whenever we say databases, um, so we are always so we are always um, stuck with three things, right? How reliable the system is. So reliability is a very important parameter. How scalable it is, and then maintain how easily can be maintained. So these are the three most common parameters that we read, right? Now many applications today are data intensive as opposed to compute intensive. Now, raw CPU power is rarely for limiting a factor for these applications. Bigger problems are usually amount of data, complexity of data, and speed at which it's changing. Now, data intensive applications typically built from standard building blocks. Okay, so now what he's saying is mostly applications that we use are data intensive rather than compute intensive, right? So, whenever we are building a data intensive application, there is three things that we need to take care of, right? First is basically we need to store data. So if it's a data intensive application, we need some mechanism by which we'll be storing data. So this is where databases come into picture. Second is basically so if it's a very expensive operation and we are trying to perform it multiple times, then again we are wasting something, right? So then we are wasting speed, right? So we need to cache. So here is when caches come into play. Now then is when we are allowing users to search based on some filter, right? Based on some keyword or some filter. So this is basically related to indexes. The fourth point is basically now, for example, if you are sending messages from one point to the another, right? So how synchronously how we are having handling the data, how are we processing? So basically stream processing. The last is basically periodically crunch a large amount of data accumulated. That means periodically giving data or batch processing. So fifth is batch. Now it sounds painfully obvious that just because these data systems are such a successful abstraction, we can think them without thinking too much. When we build application, most engineers won't dream of writing new data storage engines from scratch because data versus okay. So we already have pre-existing databases, right, that we can use. But reality, there are many databases with different characteristics because different applications have different requirements. Now there are various approaches to caching, several ways of building indexes. When building an application, we still need to figure out which tools and which approaches are the appropriate. This book so will the journey through both the principles and practicalities of data systems and how we can use them to build data intensive. We shall so basically what is telling that there are different types of databases already available, right? So how should like instead of building our own database engine from scratch, we will use already these are pre-existing systems, right? So which database to use for which functionality is what are we going to do, what we are going to see. Now thinking about data systems, when we think of databases queues, it's very caches etc, being very different categories of tools. A database and a message queue have some superficial similarity, both store data for some time. They have different access patterns, which means different performance characteristics, thus very different implementations. Now, so why should we lump them together in a so basically now we are trying to understand data systems, right? So there are different types of databases. So which to use what? The many tools have optimized, they are optimized into a variety of use cases and they no longer neatly fit into a traditional category. For example, there are data stores that are also used as message queues, the like Redis. There are message queues with databases like durability guarantees, for example, Apache Kafka. The boundaries between categories are becoming blurred. Secondly, increasing many applications now have demanding or wide-ranging requirements that a single tool can no longer meet. Okay, so what he's trying to say is right now like with the applications becoming okay, when you combine several tools in order to provide a service, the surface okay API handles this implementation. We have successfully okay now so in this book, so basically what he's trying to say is there are so many types of databases, although each database has a specific what do you say cleared boundaries, but then with our applications becoming so data intensive, it's very confusing to use which system or to which data that we know or which database that we should be use. Now for so basically for these things we are having three rules, right? One is reliability, scalability and maintainability, right? The reliability is something that is reliable, that means performs the application as so first the first key point that we think is how reliable is our database. Again, basically this is related to performance. If the performance is good enough under expected load and volume, if there is any so is the system capable of handling any unauthorized and abused access, is it capable to give proper results when there is more than the expected load, or when when under the expected load, is it working well or not? So that is basically reliable, right? If all those things means together working correctly, then we can understand reliability as meaning continuing to. So basically, this is um, working correctly is what we are dealing here. The things that can grow are faults, and systems that anticipate the faults are called fault tolerant or resilient. The former term is slightly misleading. We may make a system tolerant of every possible kind of. It's not possible to we could make, but that in reality, you in practicality, you can have number of results, right? But it's very difficult in practicality to have that. To have a 100% fault tolerant system. Okay. Now, note that a fault is not the same as a failure. A fault is basically some component derivating spec from its spec, whereas failure is something. And when okay, so there is a difference between fault and failure. Fault is some an issue. Failure is completely falling down. Continuity its font on we can make sense to increase the rate of falls by triggering them deliberately, for example, by random killing individual processes without warning. Many critical bugs are due to poor error handling deliberately. Okay. Now, hardware falls. Now, when we think system failure, hardware is what comes into mind. For example, disk crash, RAM becomes faulty, power grid has blackout, some other unplugged the network cable. Or anyone who has worked with large data centers can tell you these things can happen all the time when you have a lot of machines. So hard disks are reported to have a mean time of failure of about 10 to 50 years. So on a cluster with 10,000 disks, we expect an average one disk to die per day. Now, faults is now when we talk about failure. So basically, we are talking about two things, right? So issues, what can happen is basically one is a fault. A fault is not a fail complete. So there is a thin line between fault and failure. A fault is completely offline, like not able to deliver our service. So that is something called as failure, right? Complete failure. Our fault is not a complete failure. There, it's like a thing that can be like, for example, it is something uh, that is coming from its specification as well. It's coming from it's derived from the specification. So now hard disk. Now, how many when you talk about failures, basically is we talk about hardware, right? RAM becomes so hard disk. Uh, so hard disk basically have a mean failure time that is about 10 to 50 years. If you are storing with 10,000 disks, then we can say that one every, so on an average one disk per will die per day. Our first response is usually to add redundancy so that now this is basically when you are having this may be set up in a RAID, or you can have different types of configurations, right? So that the hardware does not fault. Ultimately, whatever your data is, it is going to be stored on a hardware, right? Now, until recently, redundancy of hardware components was sufficient for most applications, making it failure of a single machine fail. So we have redundant systems, right? So what if one thing's fail? Now, thus multi-machine redundancy was only by a small number of applications for which high availability was absolutely essential. Now, so as data and computing volume have increased, now we have moved towards cloud platforms such as AWS, and then we have, for example, we are not actually having the rack, right? Basically, we are using a cloud provider via internet, right, to access database, and the advantages of that is it is like you can scale them on the go, right? Now, platforms are designed to prioritize flexibility, elasticity over a single. So instead of having a single machine, what we do is we store data on different machines. Now, when we think of software errors, hardware fault is being random. One machine disk failing does not imply that the machine disk is going fail. They may be due to weak correlations. For example, a common cause is basically temperature in the server, right? Like otherwise, it is unlikely that a large number of hardware components will fail. Another cause of fault is systematic error within systems. Such faults are harder to anticipate. And okay, a software bug is something, for example, that causes the instance to crash when. Okay. Now human errors. Now humans design and build software so they can be outages, right? One study of internet source found that the configuration errors by operators were leading to the outages. Whereas hard faults, for example, a server fault or a hardware fault was very uh, what do you say? Uh, very rare, right? So now one way to overcome human errors, basically we try to decouple our logic, right? We don't. So we try kind of follow the solid principles where decoupling or loose coupling is our main goal, right? Uh, so by doing that, what we are separating is human errors um, from happening. Now, important reliability is not just a nuclear power, so scalability. Now, even if a system, now then let's come to the second point, that is scalability, right? Even if a system is working reliably, it doesn't necessarily work that it might work again. For example, initially, for example, when we talk about scalability, basically this is something unexpected, right? What if our user base goes on a very large scale? No, this is where, so reliability is when we are expecting that many people to come. Re- Scalability is what if we got more number of people coming in. first we need, okay, describing load. Now what is the load on the system? If we can discuss growth, what if once our load doubles, then we can configuring different parameters, right? Load parameters. So scalability comes in there when we are respected, when we are dealing with uh, load, right? When load is a where there is a sudden increase in the capacity or the number of users accessing. Now maintainability. Now major of the software development cycle is going to be maintaining our code. Okay. So this is like a very brief overview of what are we going to talk about. So what are the three things when we say in a system, what are the three hard parameters that we look for? One is so reliability is when how accurate the response is. Mm, uh, so when we say about how so first is reliability, right? So basically this is relating to so like how so reliability is when we know like what is the load, right? When we know what the load is. Scalability is something that what if the performance increases, like for example, what if the number there is a sudden increase in the number of users, is our system able to handle that? The next thing that we have is maintainability, right? This is basically related to test cases and whether it is basically this is towards more coding side, I feel. So these are the three. So whenever you talk about systems, these are the three major things that we tend to uh, understand, or we tend to something. These are the three main things that we tend to check, right? Uh, okay. Now data models. Now this is something very. This is very. So now we will be studying about what how are now we will be talking about data models and query languages, right? So data models are perhaps the most important part of developing a software because they have a profound effect not only on how the software is written but also on how we think the problem that we are solving. Most applications are built by layering one data model on top of the other. For each layer, the key answer is how is represented in terms of the next lower layer. For example, an application, you look at the real one, which there are people, organization, goods, action, money flow, sensors, and model it in terms of objects or data structures and APIs that manipulate the data structures. Those structures are often specific to your application. When you want to store those data structures, you express them in terms of a general purpose data model such as JSON or XML, tables in a relational database or a graph model. The engineers who built a database software decided on a way of representing that JSON XML relational graph data in terms of bytes in memory or disk on a network. The representation may allow the data to be queried, searched, and yet hardware engineers have figured how to represent bytes. Now, in a complex application, there can be more intermediate levels, but the basic idea is still the same. Like each layer hides the complexity of the layer below it. The abstraction allows us. Okay. Now, the best known data model. So, data model is basically okay. So, in our okay, now let's what is it trying to? So, basically, this is data model and query, right? So, if this is my application, the data inside this application will be for that I will be using some sort of data structure, right? The data structure that can be any data structure. It can be a linked list, or it can be so inside the application is when we are dealing with data structures, right? So inside, so the moment you say about data structure, you are inside the application, right? We haven't gone anywhere to store the data. The moment we want to store the data is when we come, so when we decide, right, how to store the data, like how will how, in what format would I be storing? Would I be storing it in JSON? Would I be storing it in XML? Would I be using a relational database or any other, or would I be using a graph? So these are basically data models, right? These are indicating how the data is being stored. This is basically like how my data will be arranged when I'm looking to store it somewhere outside of the application. Now, query is basically how to okay, from these database, from the model that I have selected, how will I be getting or retrieving my data? That is basically querying, right? So query is like a question you ask. Now, our goal is basically to understand relational databases, right? I mean relational data model, right? So first, let's understand why did we come up with this model. The base model is basically probably that of SQL, server query language, which is based on RDBMS. That was proposed by Edgar Code. The data is organized into relations called as tables, right? So now now we are coming to towards our data model, right, which is RDBMS. So it was designed by Edgar Code in 1970s. Now what the way data is stored is the data is stored in relations. Now what do you mean by relation? So relation is nothing but a table, right? So AML relation is nothing but a table. A table is called as a relation. Now the relational model was a theoretical proposal and many people at that time doubted whether it could be implemented. However, by the mid-80s, RDBMS and SQL have become the tools. Now it has been there since 25 to 30 years, basically, which is an eternity of computing, right? So like 25 to 30 years is since when we are using RDBMS. The roots of RDMS lies in business data processing, which was performed on mainframe computers. Now, the use case appeared ordinary, right? From today's perspective, typically transaction processing. Okay, so the way RDBMS came into is because at that time there was a lot of transactions, right? So you used to store. Basically, maintaining ledgers was a headache, right? Uh, for example, sales or bank transactions, the airline reservation, stock keeping, batch processing. Other databases at that time forced application developers to think a lot about the internal representation of data in the database. Right? The goal of RDBMS was to hide all those internal things and um, uh, behind a cleaner interface. Right now, over the years, there have been many computing approaches, data storage and querying. The network model and the hierarchical model were the main alternatives, right? But the relational model came to dominate them. Object databases came and again in late 80s. Now XML databases appeared in early 2000s. Now each computer to the relational model generated a lot of hype in its time, but it never lasted. So what he's trying to say is RDBM is a legend, is a goat of databases. It's the greatest of all time invention. So in the early 2000s, we came with JSON and XML, right? But then still, it was very difficult for them to overpower RDBMS model. And remarkably, RDB relation databases turned out to be generalized well beyond the original scope of business data processing to a broad variety of use cases which are still used in today's web. Be it in online publishing, social networking, e-commerce, software as a service, anywhere. RDBMS is still being heavily used. The NoSQL. In 2010, NoSQL is the latest attempt to overthrow the RDBMS. The NoSQL is unfortunate since it does not actually refer to any particular technology, right? So whenever you talk about NoSQL, basically it is not referring to any technology. We say uh, like we don't want SQL. Basically, we are saying no RDBMS. That was originally intended to symbolize a catchy Twitter hashtag for a meetup. Nevertheless, the term struck a nerve and quickly spread. So initially, it was started through Twitter, right? So it was a hashtag that was like, let's not use SQL. So time again, people try to overcome database RDBMS, right? Now, number of interesting databases are now associated with the NoSQL hashtag, and it has been retroactively interpreted not only SQL. So basically, we say this is not only SQL. First, now I need. So there are several driving forces. First is scalability, right? Greater scalability than RDBMS can easily be achieved. Widespread performance for free and open source specialized query operations are not well supported in RDBMS. Now, RDBMS also has its kind of its drawback, right? Now, the object relation mismatch. Now, most application development is an object-oriented language. So, basically, would be most languages that we use, whether so for development, you would be using some sort of language, right? So, it will be Java, it can be Kotlin, it can be Swift, you can be using JS. So these all are heavily OOP or object-oriented programming language, right? Because they follow OOP paradigms. They're not so each of the language may not follow all the OOP pattern, but they are classified as OOPs because major of the things is done by OOP. Or they follow major OOP aspects, right? So now one biggest drawback or biggest issue with RDMS is since application development is OOP, SQL is not a OOP language, right? If the data is stored in relational tables, it's a awkward translation. So if my language is ultimately it's the application that is going to use the data from the database, right? So what he's trying to say is if my language is heavily object oriented or OOP oriented, and my NoSQL is related to tables, right? So there is a very uh, there is a very odd matching that we need to do, right? So most of our applications are built using this, right? So remember RD, so SQL is databases will so my RDMS is the most famous way to query BMS is using an SQL, right? Server query or SQL query, however you say it. Now, so the other thing or the why no SQL was so much in this our application is based on an OOP language. Now, however, SQL is based on tables, right? So we need an intermediary to have this OOP to table thing, right? And an awkward transition layer is required. Now, the disconnect between the models is sometimes called as an impedance mismatch. So, impedance mismatch is something. So, this is called as for. This is. What do you say? Uh, what do you say? So, impedance mismatch is not a uh, computer related thing. It is basically something called as stum matching, right? So, the. I'm not sure, but then I guess it's related to some. You achieve high power, but. Oh, I guess that's the. So impedance matching is basically to ensure that there is sufficient power, transfer of power, and sufficient integrity of signal when we do uh, load and from from when we are transmitting and towards the load, right? So we need to make sure that there is a sufficient amount of power being transmitted, right? So whenever you are transferring powers there should be no mismatch occurring. I mean, sufficient power should be delivered so that the way the sufficient power delivered is something called as impedance matching, right? So it's basically no. So for the same thing, so why he's saying there is an impedance mismatch is because our language applications are developed on an OOP, databases are on tables. So SQL is basically dealing with tables, right? So there's a lot. A transition layer has to come in picture, right? Uh, which will convert this OOP to this table, right? So then for that we have something called as an ORM or Object Relational Mapping. Now, for example, we have Hibernate. Oh, this is a very famous Java. What do you say? It's a very famous Java application, and basically what it does, it reduces the amount of boilerplate code required for this translation layer, but they cannot completely hide the differences between the two models. So basically, you have, so this is very famous in Java. Hibernate. It's a very famous application. Then the next thing that we have, there is something called as active record as well. This is another ORM, basically working on the translation layer, right? So this is basically, yeah. This is again an ORM, right? That does that matching very or translation. For example, now let's see. For example, our resume could be expressed in databases. The profile as a whole can be identified by unique number. Okay, for example, let's see. He's taking an example of how LinkedIn is going to use RDBMS, right? So first is the unique, right? So for unique identification, you need something called as an ID. You can have one column for ID. The next you can have is basically what all do we have in a resume. You will have be having a first name, you will having a last name, years of experience maybe. However, most people have more than one job in their careers, and people may have varying number of periods. So there is a one to many relationship from these users which can be represented in various ways. In the traditional SQL model, the most common normalized representation is to put positions. Okay, so uh, then the data versions of SQL standard support for structured data types and XML data. This is allowed multi-valued to be stored within a single row with support for querying and indexing inside those. Now these features are supported to varying degrees by Oracle, MS SQL, JSON data type is also supported. A third option is to encode jobs. Okay, so even if it's a database, at the end it's basically an hardware, right? That is going to, for example, oh, for a terrestrial which is nothing self-contained documentation representation can be a quite appropriation as the appeal of being much simpler than XML. Document-oriented bases like MongoDB Rethink support this data model. Oh, so yeah, it's a lot of thinking that has to come into picture to say what kind of database are we going to use and why do we use. So now what uh, what SQL is, so basically SQL is nothing but um, uh, our whole main goal is basically to study the relational data model, right? So you may have more than one relation possible, right? So someone could be so there are a lot of different types of relations that are possible, right? So as I said, so basically, and to a very lower level, if you see databases, are nothing but hardware, right? So hardware will store the information, right? Okay, so let's say, uh, so this is the hardware, right? Now this can be anything. It can be a SSD, HDD, whatever type of disk you have. So this could be SDD, a solid state device. It could be a SDD. This is where you are going to store data, right? Now, uh, so basically, now how will the data be arranged here? Um like how will I be arranging the data here is what I am. Uh, so like how are we going to store our data is what is data models, right? So basically, data is stored on the hardware. So how it is stored is what we are worried when we come with two databases. How it is stored on our hardware is what our data models come in. How these data models can be accessed is something a query language. But if you think data on an hardware will be stored in form of 1 and 0 itself, right? So at the lowest level, it will be stored on 1 and 0, right? Okay, so if you see data representation, uh, you can classify data into more complex thing, right? So basically, first is something the application layer, right? This is the application layer or the user level layer. So here is the where the user is present. Then we have something called as a database layer. Now this database layer is basically you going to model our data based on the model we have selected. Now then we would be having something called as then we have a storage engine, right? So the storage engine is basically going to convert it into ones and zeros. This is hardware language, right? So here is when we come to hardware language. and then we have like files on a disk, or how we are organizing, and then is basically then is my going to be my actual entity, right? So actual physical device, whether it is stored on disk, whether it is an electromagnetic disk, or whether it is a solid state device. So we are present over here, right? So we have our model, so we are going to retrieve the data from our model, and here is when our query language will come into play. A database model lives in the software logic of database engine. Basically, um, okay, so in the database engine's logic, so physical bits and the SDD, or whenever you come to the hardware, is basically one and zeros. The data model is basically how it is stored in the database's engine's logic, right? That is much at the software level. We haven't gone straight to the hardware, so we are still at the software level only. Then we go to the binary representation, that is in the engine and disk, and then is physical 1 and 0, that is the storage, right? So this is how the physical representation is going to work, right? But then suppose we have an application, right? So we need to, okay, so but don't we, so like SQL is basic. Oh, now this is I'm going to work both querying and inserting into the actual table. So it's one is going to query and one is going to insert. So data modeling software is, what I'm trying to say is, if there's an application that is running, so how will uh, that RDBMS, So don't we want to use any software? No, I'm trying to understand at the app level how things are working, right? When I say locally, I'm using the mobile hardware. Okay, I got that. Oh, so SQL is. Oh, yeah. Okay, now I guess what it's trying to say. So our goal is to add and our. In tabular format only, right? We need to make sure this is going to happen. So what we are going to do is this is the application, right? So if it's an Android, it will be written in let's say this is an Android application that we are running, right? This will be written in Java, Kotlin, or some other OOP, some OOP based language, right? So we'll be using some interface here or some ORM that will link this to a software which uh, which interacts with only relational or tabular data format. So that software is basically nothing but called as SQL, right? So this ORM is going to communicate to the SQL. Now SQL is going to make sure that the tables are being created and uh, at the database level we have the tables created, and then we are going to then this is after this is what is so this is right now we are still at the SQL, right? So we have insert, then we are going to go to the ones and zeros, right? Eventually which is going to go to the HDD, that can be electromagnetic, that can be solid state or anyhow, right? So it's SQL. That job of that SQL is basically to maintain that when SQL is going to contact a database engine like SQLite. The SQLite is what is going to create the tables. It's an engine because some sort of processing is happening, right? Some sort of CPU time it might take. Like what if we try to use some other type of data model? Okay, so nowadays database have so by default SQL will not store, like we will have to convert it into some text format or something else. Yeah, we can do JSON to text and then we can parse it again as JSON back. So when we say relational databases, basically our data is going to store in the form of tables and columns. The way that we are going to do is to query or to work on that data, we are going to use a software called as SQL. That SQL is going to be go to and pass to an ORM, because our object oriented our languages will be application developed will be in an object oriented language, right? So from there, that ORM will translate it to the SQL and then SQL will contact to the engine. So now uh, this is something that we generally install, right? Okay. No. Do we use SQLite? Oh no. Yeah, MySQL is what. So when I install MySQL, am I installing any engine or something? Oh yeah, you have. Oh, is it a okay? I see. Also, we need to mention which port are we running the actual RDBMS. So client will send an SQL query to the server. Server will go to the uh, let's say different types of uh, engines. There is InnoDB, Postgre, Oracle, Microsoft, MariaDB, a lot of them there is. So the engine is actual tabular data. Okay. Yeah, so that's all for this session. I hope you guys liked it. I'll see you guys a little more on in detail in the next one, and then we'll go on from there. So yeah, this is the first session to database and a brief introduction of how and when our applications are going to work. So yeah, that is all for this. Hope you guys liked it. Please subscribe to my channel, and then I'll see you guys in another video with another important. We'll continue SQL. So that's all for this session. Please subscribe to my channel and see you guys in the next one. Till that time, take care. Bye bye.